Okay, so now let's go over the solutions for the other questions in the quiz. In addition to what I posted the video for question number 3. Okay, so let's go through question 1. Now, I wanted you to suggest how would you distribute a secret key or a message between two users using public key encryption so that you can guarantee both confidentiality and integrity. So, by confidentiality, what we mean, whatever you want to send should not be looked at by any other user other than the receiver or the intended receiver. And by integrity, what we mean, whatever we send should not be uh, uh, able to be changed, or in other words, the receiver should not get something which the sender did not want to send, and the receiver thinks that is what is being sent. So we should not make the receiver to believe that what it receives is really what the sender wanted to send. The receiver should be able to make sure that it is what it is receiving is what the sender wanted to send. All right. So in order to guarantee integrity, we have to use a hash value if you want to make sure that the message came without any corruption. All right. So the thing that I suggested you in class is to compute the hash value, and so just computing a hash value will guarantee you the integrity, but how do you make sure it is coming from the sender, right? So you encrypt that with the private key of the sender. So this is like a digital signature now, because the message came, it is the message, the hash value of the message is encrypted with the private key of the sender, right? Because only the sender can do this, nobody else can do this. Now the sender um, wants to send the message, so now it puts the message along with this. Okay, so the message along with the encrypted hash value, the whole thing is encrypted with what? With the public key of the receiver. So the message along with its encrypted hash value is encrypted with the public key of the receiver. So when this is sent, what happens? Only the receiver can decrypt or do this outer level of decryption. Alright, so which means nobody else except the receiver can decrypt this, so that provides a confidentiality. And once the receiver decrypts this, what will happen? The receiver will go ahead and access this portion, because this is separate from M, right? So the receiver sees the actual message M, but it wants to make sure the message M came without any corruption, or it's not being changed, because anyone could send a message M encrypted with the public key of the receiver, because the public key of the receiver is not everyone, so anyone could send a message to the receiver. So how does the receiver make sure that the message came without any change? So for that, the receiver decrypts this portion, right, and using what? The public key of the sender, okay, and extracts the hash value which is encrypted inside. So the receiver now has the hash value and the message. So now the receiver can compute the hash value of this message and compare that hash value with this hash value. The hash value for this message should match with what is the hash value that is available here. Only if the two hash values match, it means that the message came without any corruption and it was sent by the actual sender. So this actually provides you the authentication factor also. Okay, it provides you authentication too. Okay. Now the other question: how to find the encryption decryption keys? This is the standard RSA. So given P and Q, so P is 7, Q is 11. Find N equals P times Q, which is 77. And then P minus 1 is 6, Q minus 1 is 10, so find P minus 1, Q minus 1, which is 6 times 10, 60. So the encryption key is something that is relatively prime to P minus 1 times Q minus 1. So what we have to do? We have to choose an encryption key which is at least 10. Okay, so if you choose 10, you want to make sure whether 10 is relatively prime to p minus 1 times q minus 1. The encryption key has to be relatively prime to p minus 1 times q minus 1. So is 10 relatively prime to 60? The answer is no, because both 10 and 60 are even numbers, first of all, right? So they cannot be relatively prime. What is the condition for two numbers to be relatively prime? The GCD has to be 1. Okay, so if you want two integers m and n to be relatively prime, the GCD has to be 1. So now try with 11. So 11 and 60. So let's try GCD of 60 comma 11. Now use the Euclid's algorithm is equal to GCD of 11 comma 60 mod 11. 60 mod 11 is 5, and this is equal to GCD of 5 comma 11 mod 5, which is 1. GCD of 5 comma 1 is GCD of 1 comma 5 mod 1, which is 0, and GCD of 1 comma 0 is 1. So they are relatively prime. So we have found the encryption key, which is 11 comma 77, right? Now we want to find the decryption key. So we use what? The extended Euclid's algorithm. So this is your M, this is your N, 60, 11, and then this is your P and Q. So let me write all the stuff here. M and N. So this is X and this is your Y. So we want to solve what? To solve 60x plus 11y equals 1. So we want to find x and y. Actually, now we want to find what? The multiplicative inverse. The decryption key is nothing but the multiplicative inverse of the encryption key, okay, in class modulo what? P minus 1 times q minus 1. The decryption key is the multiplicative inverse of the encryption key in class modulo p minus 1 times q minus 1. So which means we need to find the multiplicative inverse of what? Encryption key is 60 in class modulo, sorry, encryption key is 11, right? Class modulo 60. So that's what we are doing here. Solve 60x plus 11y equals 1. So you want to find the multiplicative inverse of 11 in the class modulo 60. So we are actually interested in the value of y. So go to the extended Euclid's algorithm. So 60, 11, and then these are the initial values 1, 0, 0, 1, and this is empty. So what we are going to do is find the quotient. 60 divided by 11, the quotient is 5, the remainder is 5. So this term is going to be 1 minus 5 times 0, which is 1 minus 0, 1. 0 minus 5 times 1, which is 0 minus 5, which is negative 5. Then 11 divided by 5, the quotient is 2, the remainder is 1. And then 0 minus 2 times 1 is 0 minus 2, negative 2. 1 minus 2 times negative 5 is 1 minus 2 times negative 5 is 1 plus 10, which is 11. Okay, so we got 11. So 5 divided by 1, the quotient is 5, the remainder is 0, right? So we got this 11 over here. So this 11, the value of y, is what? The multiplicative inverse of Again another this 11, so 11 is the multiplicative inverse of 11 in the class modulo 60. You can verify it. 11 times 11 is 121. 121 mod 60 is going to be 1. Okay, we went over this in the video. Now the Diffie-Hellman key exchange problem. You have Alice and Bob agreeing to need to agree on a secret key. So the field size, which is n, is 45. The value of the integer g is 8. So what is the idea behind the Diffie-Hellman key exchange? Alice sends, let me see if I can pull up the material. Okay. Okay, so Alice sends g raised to a mod n, okay, to Bob, right? So let me see, I think I should be able to draw this. Okay, so we have Alice and Bob. So now Alice is generating locally A, and both of them know that G and N, so they know G and N. Okay, alright, so Bob generates B and he knows G and N too. So now what happens is Alice computes g raised to a mod n. So this is g raised to a so Alice computes this, okay, and let me, so she sends this to Bob, okay, sends this to Bob. So Bob has this, right? So now Bob also has what with himself? Bob has the B, the secret integer that he generated. So now what happens? Bob can compute g raised to a, the whole thing raised to b mod n. Okay, so Bob can compute g raised to a, the whole thing raised to b mod n. Now same thing happens at the Alice side. So Bob can compute what? Bob can compute independently g raised to b mod n and send this to at the same time. Okay, so actually this should go so as Alice is sending her information, so let me put it over on the channel. So Alice is sending her information, Bob is sending his information, g raised to b mod n. Okay, so Bob sends this to Alice. Okay, so as Bob can locally compute this, Alice can also locally compute what? Once she gets g raised to b mod n, all she has to do is compute g raised to b, the whole thing raised to a. Okay, so she gets this g raised to b from Bob, then g raised to b, the whole thing raised to a mod n. Okay, so let's do this example. So we want to compute 8 raised to 5 and then the whole thing raised to 7 mod n, which is 8 raised to 35 mod n. So for 35, what we are going to do is compute 8 to the power 1, 2, 4, 8, 16 up to 32. Alright, so 8 to the 1 is 1, 8 to the 1 is 8, 8 mod 45 is 8, 8 square is 8 to the 1 times 8 to the 1, so it is 8 times 8 mod 45, so it's 64 mod 45, 64 mod 45 is 19, 8 to the power 4 is 8 square times 8 square, 8 square mod 45 is 19, so 19 times 19 mod 45, that's going to be, so how did you get this? This is 8 times 8 mod 45, which is 64 mod 45, which is 19. Now here it is going to be 8 square times 8 square, so 8 square is what? 19 times 19 mod 45, that's going to be 361 mod 45, which is 1. And then this is going to be 8 to the 8 is 8 to the power 4 times 8 to the power 4, so it is 1 times 1 mod 45 is 1. So once you get a 1, you keep getting 1, right? So 8 to the 35 mod 45 is 8 to the 32 times 8 square times 8 to the 1, because we want to write 35 in binary, and 35 in binary having exponents 32, 2 and 1, adding together you get 35. And 8 to the 32 mod 45 is 1. 8 square mod 45, just saw it as 19, and 8 to the 1 is 8, so this is 1 times 19 times 8, 19 times 8 is going to be 152, 152 mod 45 is going to be 17. So this is a secret key Alice and Bob have agreed, and if Bob has to do that, what he has to do, 8 to the 7, the whole thing raised to 5, so but it's still 8 to the 35. Okay, so either way you should get the same thing.